All right. Hey, everyone. I hope you got some coffee in your system. So for session one, we'll have 6 registered reports. We'll have 10-minute presentation, 5 minutes questions, and then, so I guess I'll start by introducing the first author, Kabilan, who will talk about TENSURE fuzzing sparse tensor compilers. So yeah, take it away.
Hey everyone, so I'm Kabilan. I'm from Virginia Tech. So I'm working with Professor Kirshanthan Gulzar from Virginia Tech. And the tool I'm presenting today is called TENSURE. This is about fuzzing sparse tensor compilers. So I'm more of a compiler person than fuzzing person. So before getting into the fuzzing terminologies, let's get some understanding about tensor compilers and sparse tensor compilers. So that let's focus on tensors first. So what are tensors? Tensors are multidimensional arrays to represent modern data for different computational fields, from data analytics, machine learning, through scientific computation and simulations. Traditionally, these operations are handled via hand-optimized libraries, or prototyping tools, or maybe dense tensor compilers. But the problem is, these tools which handle these tensor operations usually don't handle the main aspect of the modern tensor data, which is sparsity. So what are sparse tensors? To understand it, let's take an example of Reddit user comments tensor data, which is a 3D tensor data of 82 exabytes of data, which is extremely large. But if you take a closer look at this data, only about 35 GB are actual non-zero values, non-empty values. Others are, the remaining data are just empty zero values. So this extreme level of sparsity is exactly why we cannot treat these tensors like a traditional dense arrays. Otherwise, we will be wasting a staggering amount of computation and also the memory on these zero values. So one solution for it is to use different compression format. But the problem is, the moment we introduce compression format, the tensor computation become complex because of to iterate through this different compression format. To understand it, let's take an example of a tensor operation called matrix-matrix multiplication, and number of program variants that we can write based on available compressed formats. Let's say we only have one compressed format, CSR, then all the tensors A, B, and C will have to take the same compressed format, which ultimately gives us only one program variant. The moment we introduced another compressed format, let's say CSC, now we have 2 options for each tensors, which ultimately gives us 8 program variants. The moment we start to introduce more and more compressed formats, the number of program variants start to increase rapidly. Here I'm not considering the different program schedule that we can look into. This, so this exponential increase in this number of program variants cannot be scaled by these hand-optimized libraries. Therefore, a compiler-based approach is formulated, hence the sparse tensor compilers. The task of the sparse tensor compilers is to iterate through different compressed formats in an effective way to do tensor operations. Now that we understand about the sparse tensor compilers and the importance of the sparse tensor compiler and also the complexity, let's look at how we can test these compilers. One of the well-known and widely adapted technology for testing compilers is metamorphic testing. So let's see how metamorphic testing works for testing compilers. We initially start with the seed program, and we use the compiler under test and compile this program and execute it and get a reference output. Then we create equivalent programs which should be semantically equal to the seed program, and we use the same compiler to compile and execute and get a output from it. Now that we enforce the semantic equivalence between this seed program and the equivalent program, we expect the output to be equal to. If it doesn't, we can say there's a bug in the compiler. So let's see how we can integrate this for sparse tensor compilers. So we need a seed program. So we can build a random program generator which can generate a program for you. Let's say we are testing a compiler called Taco compiler. We can generate a program like this, which is for matrix-matrix multiplication, and the Taco compiler can compile and execute it. The next thing we need is equivalent programs. To get equivalent programs, we can create mutation operators which take this seed program and do semantic preserving mutation to create equivalent programs. So the critical part here in stress testing these compilers depends on these mutation operators. So we have defined a few mutation operators which are very specific for this sparse tensor compiler, which the first one is called storage format heterogeneity. So what it says is, irrespective of which storage format you use for the computation, the output should yield the same result. For example, let's say tensor B, which is represented in CSR format. If you change that to CSE format without changing the computation, it should yield the same result. This is one of the mutation operator. The next mutation operator we have is algebraic commutativity, which is exactly what it sounds like, which is the commutative law of commutative law. We can take these tensor operations, and using this commutative law of multiplication, we can change this order from A is equal to B into C to A is equal to C into B. Now that we have the reference program and also the mutated program, we can move to the execution phase, where we take these different programs and use our compiler, the target compiler, and compile the program and execute it. Crucially, we need to save these results so that our metamorphic oracle, which can inspect and compare these results to find any discrepancies, and if it finds one, it flags a bug. But are those enough to test Sparse tensor compilers? Not really, because if you take the Taco compiler, which is written in C as a DSL on top of C++, so if you were to implement this random kernel generator and the mutator specific for Taco, that means we have built a tool to test Taco compiler. So if you were to test Finch compiler, which is written as a DSL on top of Julia, then we have to rebuild this entire structure from scratch. So doing this for every compiler is not practical, not scalable. So what we can do is, in this work, we are introducing an abstraction layer, which we call INSUM notation. So what these INSUM notations are, a representation to extract this tensor operation as much as possible. For example, we can take this general matrix multiplication in this summation notation, and this converted this into an INSUM notation. So this green thing that you can see is the INSUM notation. I don't want to go into the low-level details of these INSUM notations, but this is a very well-established mathematical notation for representing tensor operations. So when we introduce this abstraction layer, there comes two more problems. Now we cannot take this abstract program and directly run it with the compiler. Oh, okay. Okay. So we cannot directly take this reference program, which is an abstracted program, and to run it in the compiler. We need compiler-specific code. So we're introducing a translator mechanism, which can take this abstracted program and translate it to compiler-specific code. Then one more problem is, now the random program generator is not going to generate a compiler-specific code. It's going to generate this abstracted program, which is an INSUM notation. So we need to generate these INSUM operations. So how do we generate these INSUM operations? So our first thought was to use a grammar-based fuzzer. So we can define set of grammars and use this tool called Grammarinator to generate this INSUM notation based on the grammar. But the problem is, this INSUM notation is not context-free grammar. They are context-sensitive. So these grammar-based fuzzers or generators usually rely on the grammar of the language that we are testing, not the context sensitivity or the context sensitive rules of the grammar. So when we try to do this with grammar-based fuzzer Grammarinator, we only were able to generate about 3.3% of valid INSUM notation, which is not practical for fuzzing purpose. So we went ahead and built a custom solution for generating valid INSUM notation. And also, I will not go into the low-level details of how this the generation algorithm works. So with that, we can go into our preliminary results with this tool. And we integrated this to two fuzzers, which are Taco and Finch, and ran it for 6 hours of fuzz cycle, which is really low for running fuzzers. But the results are here. You can see we found more than like 5,000 miscompilation bug in Taco. But I want to be clear here, this is not 5,000 different and unique bugs in the Taco. Problem is we are doing a black box fuzzer. So even for different program input, we might be triggering the same bug again and again. So because of this black box nature, we cannot do a direct deduplication without actually looking into the source code of the program. The next one is Finch. You can see the same fuzz period, we only ran about 1,600 iterations, which is a performance issue with Finch for example, Finch on average takes about 181 seconds to compile and compute a program, whereas Taco takes about 63 milliseconds. So to mitigate this, we are planning to increase the fast testing periods as much as possible so that we can find more bugs in the Finch. And also, we are trying to integrate this to MLA Sparse dialect and also PyTorch Sparse. And we are introducing more and more mutation operators. The one is called transpose-based mutation operator, where we can take this iron-sum notation and transpose one axis, let's say B axis, and we can transpose to B transpose, and we make a modification to the iron-sum notation in a way to preserve the semantics of the computations. So then we are planning to evaluate our iron-sum generation algorithm with this modern context-sensitive fuzzers or program generators and see whether they can replace our generation algorithm. With that I conclude my presentation and open to questions.
All right. Yeah, we have time for a few questions. You just raise your hand. So I have a quick question to get us started. This is really cool work. I think finding bugs in sparse tensor compilers is very topical now because of all these like machine learning ops. One thing I'm curious about, so einsum, from what I recall, is a notation to describe the actual operator on maybe potentially two matrices, right? But also in the process of doing fuzzing like this, you'd probably need to generate the values of these matrices, right? To actually like initialize them with certain numbers, right? And you could potentially imagine certain numbers could cause numerical instability or something like that when you actually run them. So I'm curious how you approach this. You have program generation, which you can do via einsum, but how do you do this sort of data generation in that case?
So we also generate this random data generation, but the problem is we try to capture this amount of data as low as possible, because when we try to generate a large data, the problem becomes more complicated to run this program for a longer time. Yeah. So we want to try to minimize as possible. So we only generate about, for example, 5 into 5 matrix. So we don't like go beyond that. And also there's this another problem that we were talking about, this fault tolerance. Mm-hmm. So this we can get a lot of this false positive because of this fault tolerance, because we are dealing with floating point numbers. There can be a lot of floating false positive. So we have this fault tolerance mechanism we set up to as much high as possible, to 10 to the power minus 3, mm-hmm. to have to reduce the false positive as much as possible. But we are trying to move to use integers instead of floating points, because this floating point doesn't have any special connection with the sparse tensor compiler. So
I see. Okay. Yeah. Thanks. Any other questions? Do you have any sense of what types of, in your preliminary results, what types of these miscompilation bugs look like? Like, have you gotten a sense of like what types of patterns maybe are interesting for these? Yeah.
We actually listed some of the bugs in the paper and also mm-hmm. discussed about it. And it was always a logic bug in how do we initialize this. So this is like a accumulative process. You just multiply some numbers and then accumulate it. So where do you initialize these numbers? Yep. So there will be going to be multiple loops. So where do you always this problem comes in, where do you initialize this one value? Mm-hmm. So probably that's the main reason, but we cannot like pinpoint this is the program that is this bug is originating, because we need more understanding about the implementation.
Yeah, that makes sense. Any last questions? If not, we can thank our speaker again. We can start setting up the next one. All right, for our next speaker, we have Kai, who will be presenting Hardfuzz, DataFlow-Guided on-device fuzzing for microcontrollers. So yeah, take it away.
Hello, my name is Kai, and I'm from the University of Glasgow. I will present Hardfuzz, which is data flow based for fuzzy for the microcontroller. It's already been concluded by the keynote speaker. And first, I would like to give you the briefly introduction about the microcontroller. There's a diversity like software and hardware libraries in the MCUs. Like you can run like ITOS operating system. So you can, for MCUs, it can also have its own Bluetooth and the healthcare sensors. And but for this multiple functions for MCU, the design for MCU is quite simple. The CPU can directly operate the physical address for this on this chip, so it doesn't have memory management, so it's kind of risky. And but also for this kind of MCUs, the computing and operating constrained. The computing resources are quite limited. And so basically, it's very just powerful, limited board, but want to achieve the very diversity functions. Here's the most straightforward way the researcher I correctly did now, because we want to just do the file testing for the MCUs. The most straightforward way is just try to emulate the firmware. We can do like rehosting stuff on the hardware in root stuff, just try to emulate the whole process. And but if we try to emulate the firmware, it means like we will reduce the fidelities, and because the firmware is not run on the MCU directly, which means like we can't get the fully observations, and the capabilities is also quite limited. And here's the diagram shows like what kind of correctly research statement. And you can see that for the first three, like from shift to GPT-5, the first three fuzzies, they are just try to just deploy the fuzzy directly on the hardware, which means that it could achieve the best memory fidelities and execution fidelities. And so basically, it seems like we need to try to get rid of the emulation stuff. Also, for the emulation, it has its own drawbacks, because for like very simple instructions and through the CAMU, through the translation basic blocks, the basic block will just increase like 3 times bigger, and after you do some instrumentations, the size will get bigger than that. So based on that, we might want to deploy our fuzzy directly on the hardware, and we also want to provide the different coverage. So here's the data flow coverage. There's already some papers like Red Queen. They've already mentioned that data flow could provide more coverage compared to control flow. So basically, I still want to show you like benefit of the data flow. You can see from the right side of this kind of program, it's like very simple. It's like just a 3 if statement. We would like to show like generate 2 inputs to show the difference between the code coverage and the depth chain coverage. For example, if we get the input A like magic equals 0, it will go directly to the sanitizations block, and which means like for code coverage perspective, for control flow perspective, it means like I got the new code path, which means okay, I will just keep mutating based on this test case. But for the data flow coverage, because the magic definition has been changed, it means like depth chain has been broken. So for depth chain perspective, it means like this is dead end. Maybe the data chain has been broken. We should discourage the fuzzy to generate more test case based on this set. And for magic equals 1, and it's just go straight to the critical block, means that it's just another branch, and there's nothing special about the coverage. But for data flow perspective, it means like because during this process, it's go to the 2 different blocks, and it will give the 2 different rewards, provide more rewards compared to control flow. So basically, control flow can't just tell the new block but the dead data, and from the new block but the live data. And for depth coverage, it could provide more rewards if the definition have multiple uses. Okay, here's basically or what we did here, we just try to do the offline analysis, try to extract the DFU chain from the binaries. And we use like MCU's debug module mainly. It goes through the JTAG board and try to set the multiple breakpoints and try to figure out if the breakpoints have been triggered, and which means the code path will also be executed. And we just record the def and the DFU chains into bitmaps and try to get the coverage. And the algorithm is quite straightforward. First, we get a DFU diagram from the binaries, and we need the kind of weight to allocate different definitions. And we also need to just rotate the definitions and the uses. Because the hardware is quite resources limited, normally it only supports like 4 to 8 breakpoints. So we definitely need, but we have got thousands of definitions with each definitions with multiple uses. So we basically just need to swap the basic swap the breakpoints based on these functions. We invoke like base weight, which means like the highest numbers of the definitions. We also invoke like 2 penalties. The first penalty is about the local, it's about the definitions. How many times the definitions have been executed in one time, and the global penalties means like how many definitions have been triggered in the whole campaign. We also prioritize the uses. The uses is ordered by the distance between the definitions and the uses. And for bitmap, we have like the first bitmap could record the definitions. The second bitmap could record the DFU chain. Here's the evaluation part. We execute our evaluations on the FUD bench, which is quite a standard benchmark, and we compared our method with GD FUD, which choose a different method to try to allocate the breakpoints. The results looks like for emulation perspective, our tools achieve higher basic block coverage on most targets, and we get some unique basic block over. It's a diagram shows that, yeah. And for the hardware directly, we just conduct our experiment on the Arduino Duo, which is quite cheap one, and we also compared with GD FUD, which covers like 14 to 40% of basic blocks in 24-hour campaign, and here's the results we got. Okay, here's the limitation and the future work. Definitely, I just crossed the paper like a couple of days ago. It definitely there's because for now I need to set up the communication between the MCUs through the debug port through a JTAG link. I bought some dodgy version from the eBay. It's called like J-Link, but the original version is quite expensive. So there's definitely some work could optimize the debug link latency, this kind of stuff. And the DFU extractions could also be like optimized. And we also not just consider about the metrics about the control flow, but we also need to think about the data flow. And as I said before, we need to reduce the overhead during the communication between the GDB and the MCUs. And we also need to think about combine like tracing support mechanism like ETM or Intel PT, this kind of stuff. And we need to conduct more baseline and benchmarks. Basically, this work is just working in process. And please, if you have any suggestions, just let me know. Thank you so much.
Any questions? So I'm curious. So you've done all this great work on adding the diffuse extraction, identifying this sort of weighting approach to balance the hardware constraints that you mentioned. Do you think any of these insights that you might have gained can apply to maybe fuzzing in any other domains?
For now, I only think about MCU, that's kind of stuff, but in other domain, that definitely could be achievable. And there's also very mature tools like Red Queen or DataFlow, but they they already kind of achieve that for like from source code level and binary level. Yeah.
Yeah, that makes sense. When you mentioned that you compare against more baselines, do you know what types of baselines you're looking at, or?
Yeah, just like data flow baseline, like I mentioned before, like Red Queen. I basically need to like re-implement Red Queen to like MC version.
Oh, I see. Okay. Yeah, that seems like I think identifying where Red Queen, performs well, has limitations in other domains is also a good takeaway. Yeah.
Cool.
All right. I think we can thank our speaker.
Thank you.
Do you want to turn the mic up there? Yeah. Thanks. All right, for our next talk, I'll be handing it off to Toby, who will be talking about PogoFuzz, profile-guided optimization for fuzzing. So yeah, take it away.
All right, thank you for the introduction. This is PogoFuzz's joint work with Leon, who's going to give the next talk, and Kevin Bergolte from University Bochum. When we talk about fuzzing, really, like the thing that we do a lot is fuzzing at scale, right? Fuzzing benefits from adding scale. More compute means more bugs. And if you look at a project like OSS Fuzz, right, that's 1,300 open source projects, or more than that, at an average over 80 cores each all the time. And this is old data, right, from like 5 years ago or something. And large companies have internal fuzzing setups that are likely even larger. We can only guess at that. Someone from Google is here. But from what I've heard, they are much larger. Some of my PDF is not showing correctly. Anyway, even small improvements do matter here, as long as they scale. So when we look at improving fuzzers, how do we improve a fuzzer? Well, typically we look at this kind of chart, right? There's coverage over time, and if coverage goes up in some way, then that's good. But really that consists of two parts. How good are you at using your executions? Right? This is coverage per execution that you gain. And how fast can you execute test cases? Right? This is how many executions do you do per time. And most research tries to make fuzzing smarter, which is sort of the thing that you try to do normally. But what we try to do is we try to make fuzzing faster. And really, like, of course, there's a little bit of an idealized view, right? If you make things smarter, sometimes you make them slower, and vice versa. But it's generally worth trying to do both, right? Because then line go up even further. So if you look at the typical fuzzing loop, and most of you have seen and drawn this chart before, then you have your queue of test cases, you pick one, you mutate it a bunch, and then you execute it with the target, and then you get some feedback back. And if that's interesting new feedback, right, you've covered something new, then you keep that around, but most of the time, you're gonna throw that away, because it doesn't do anything new interesting. And this entire fuzzing loop is very well optimized generally, right? Like the fuzzer is a piece of software that a lot of people have looked at, and they've optimized a lot. But the target has been a little bit ignored, right? Because you need to be able to switch out the target, so you don't really spend time optimizing the target. But remember, the target is executed for every test case that you have, right? Which is millions or billions of executions. And if you run something a billion times, you better want it to be fast. So here is where profile-guided optimization comes in. This is a compiler technique that is like really widely used for big software projects. Right, so Chrome is optimized this way in release builds. Android is optimized this way, as far as I know. There has been like some hints that Meta/Facebook use this on their data center workloads. And what it does is it adapts a piece of software in terms of optimization to how it's actually being used in practice. So normally when you compile software, you make an educated guess about how a program is going to be used. in order to make optimization decisions. So here, this area that is nominally red shaded but not red shaded anymore is what the compiler thinks is the hot path, right? This A1B thing. But that guess can be wrong. But the compiler will use this wrong guess to make optimization decisions, in this case, some basic block ordering, but also lots of other decisions. And then your target is actually not as fast as you want it to be. But what you can do is you can do profile-guided optimization, which takes the program, you run a bunch of benchmarking tasks through it, and you figure out what is actually executed. And then you track that, and you optimize based on top of that, right? So you have some input that goes A23, and it counts up just hit counts. It's just like fuzzing, just slightly different because it's an actual full counter. And at some point, you end up with this profile. You feed that back into the compiler, and now the compiler knows, hey, actually, my hot path looks different, right? Like now it's A2B instead of A1B. So now when the compiler makes its optimization decisions, you end up with different decisions, and you end up with a faster target in general. And the core idea that we have now is that most mutations that you do with the fuzzer are not actually going to do anything different, right? If you mutate the input and you change something, you change a 1 to a 2, right? Usually that doesn't do anything. But instead, you do the same thing over and over again. So you have some input, and it runs this one common path, and you make a mutation, and it runs the same common path. And maybe sometimes you run into an error case, like some common error path. But very rarely will you actually deviate from that. So if you re-optimize for this common path that you're going through, then the fuzzing loop should be running faster. And this is what we do. So what we're doing here is we take a fuzzer, this fuzzing loop from just right now, like AFL++ in this case, and we piggyback on top of that. So we look through the target, the queue of test cases, and we pick out the ones that are likely to be used in the near future. And then we do PGO profiling. And we use this profile to recompile the target. And then we replace it sort of in place, right? We restart the fuzzing loop with the normal mechanism to replace the thing that is currently being fuzzed with a faster version of the same thing. And that is what PokerFuzz does. So in a little bit of more detail, step 1, right? We filter the queue because if you run the entire queue through this profiling binary, it's still a little bit wasteful, right? The queue contains a lot of residue from a long time ago, basically, which is not really interesting to the fuzzer anymore, which is not being used for new mutations. So we pick out only the test cases that have a high energy. Then we take this PGO profile. We take this set of inputs. We obtain the PGO profile. So we run this through a separately instrumented binary to get the profile, and we scale the profile based on the energy that the test cases have. Right? So more likely to be used means we give it a higher weight in the final profile. Then we recompile, and we do this very simply. Right? We stop fuzzing on one of the cores, and we run the build process again. But the other cores, if you have a multi-core process, they can continue fuzzing. And then once the recompilation completes, we replace it in the target. So PokerFuzz, we did some preliminary experiments, obviously. We know that PGO depends on what target you're running this on. So we decided to pick out 4 fuzzbench targets here based on the baseline execution speed that they have. Right? Is it a fast target or is it a slow target? Right? Do we already get a lot of executions a lot of time, or is it more difficult? And also, how diverse is the input set? Right? If you have a lot of different inputs, then the hot path that we had in the example earlier might not be so clear. Right? There might be multiple. Versus if you have a very non-diverse set of inputs, right? There might just be one hot path, and this might behave differently in optimization. So we took these targets and we ran this on 1, 2, 3, 4, and 6 cores, and extended for some of them to 8 in 5 trials of 24 hours each, and compared those against unmodified baseline AFL++ in the same version. So one of the questions that we asked ourselves is this process of we're stopping fuzzing, we're going to recompile the target. Does this actually cost us a lot of time? And the answer is yes, but. So on the left, you can see the executions per second that you get on systemd with a single CPU. The dips that you see is every time that it recompiles, right? It stops fuzzing, so it goes down. And on the single core, you lose over 10% of throughput just by not fuzzing for the time that you're compiling. But actually, this amortizes over time, and you end up with things turning out to be really fast, even with 6 CPUs already. So the reoptimization loss is not actually as bad as we thought it would be. And the other thing is, does it go faster? And the answer is yes. Of course, it goes faster. Well, sometimes. We found that for libxml2 and libxslt, it was actually quite a consistent speed up, starting at 3 cores, basically. For zlib and systemd, the results are mixed, right? It goes around a bit. Sometimes it's a bit slower, sometimes it's a bit faster, so we couldn't really make conclusions on that. But if you look, for example, at the libxslt 8-core run, right, even if you get 4%, right, this might not seem so much if you're used to big numbers. 4% of fuzzing improvement is an hour of extra fuzzing time if you're doing a 24-hour run, right? And if you say we're doing an eval and one of them is allowed to run an hour longer, right, everybody would complain a lot. So, open questions: can this reoptimization somehow mess with the fuzzer instrumentation? We think this is unlikely. We haven't seen this. There is also sort of a side note on different PGO instrumentation methods, right? This is LLVM AR-based PGO, but there are alternatives. And also the question of when do you actually want to recompile? And we're going to look at a subset of that in what we're going to do for final experiments. First of all, we're scaling this up, right? We saw that if you add more cores, the cost of recompilation sort of disappears. So we think this is going to perform even better if you add more cores. So that's what we're trying to do. We only looked at a couple of targets. We want to look at more targets. So we're just going to try all of the fuzzbridge targets where we can actually get PGO to work. And we want to look at also how do other fuzzers behave, because they will explore the input space differently. So they will have different queues. So maybe the diversity is higher or lower. So we want to try at least Hong fuzzer libafl also. And finally, the question of recompilation, right? We're currently recompiling once every hour, but it's unclear if that's actually necessary. Maybe we can get away with doing it every 2 hours, every 4 hours, every 8 hours. And maybe we can skip it sometimes if the queue hasn't changed a lot. That's something we're going to investigate. All right. To conclude, right, we augment an existing fuzzer and speed up fuzzing just by re-optimizing the target every time. You can find the paper and the slides online. And I'm free to take questions.
All right, thanks, Toby. Yeah, any questions from the audience?
Do you have any sense of how this performs, how much it depends on how slow the target is to recompile? Like if you're compiling a really, really big program, are you going to have lost?
So for sure, I think this is if you have a target that is really slow to recompile, you're going to run into trouble. Because just the cost of redoing this optimization step is going to exceed, you're not going to amortize that. If you have a target that compiles for an hour, right? You're not going to amortize that regardless of what you're doing. But if it's a normal, the fuzzbridge user space targets, right? They take a couple of minutes at the worst. That is much more doable. And of course, this is a trade-off. What you can also do, right? And this is sort of a more non-academic way of doing this, is you can re-optimize on a separate machine. Right? You can just continuously rebuild things somewhere, and then as you get done with the recompile, you just plug it in. That would be an unfair comparison, of course, but in practice, that might be more likely what you want to do. Right? You pull the binary from your CI or something, and you plug that in.
Thank you.
Any other questions?
There is one at the front.
Oh.
Great talk. So I was wondering whether the main cost is the recompilation or actually getting the profile.
It's most certainly the recompilation. So the profile you're running, even at a large queue, right, is might be 30, 40,000 entries. You're not running all of these through the target binary. You might run 1,000 or a couple thousand, and then most of them run really fast. Even with systemd, which is one of the slower ones, right? You get 100 executions per second, so you're through this, in 10, 20 seconds, and then you compile for another 2 minutes. So definitely the largest part of the cost of the recompilation itself.
I see. So you are not minimizing the corpus before, or doing anything
so we
like that?
We only pick test cases that the fuzzer considered interesting. If you, like a lot of the minimization tools, as I understand it, like also try to run the target binary to some extent. I'm sure there are smarter ways to like limit this even further, right? If you look at like the coverage map that they produced. But just because they produce a different like coverage map doesn't necessarily mean they behave differently in PGO anyway. But you have, if you do like the binning that AFL does, right? PGO wants to count anyway and needs to count, otherwise it doesn't work.
Yeah.
Probably there are heuristics you can apply to make this like that are a little bit smarter than just thresholding, but it might not necessarily help you a lot.
Yeah. I was also wondering if there is an overlap between the fuzzing coverage instrumentation and the PGO instrumentation, and whether maybe we could reuse the fuzzing coverage counters.
That was the initial idea, and we cannot. And the reason for this, the first reason that you will run into when you try to do this, is that the fuzzing instrumentation is built in a way that keeps the map small for speed reasons, and you will have a lot of like 8-bit counters. And those will overflow. And that's fine for fuzzing, but PGO instrumentation relies on being able to do maths between counters. And we will see more about this in the next talk. And things will break horribly if you do this. And unfortunately, that didn't quite work, which is why we're doing actually the rerunning.
Any other questions? I have a quick question. So I think early in your talk, you mentioned how kind of the idea is that when we perform mutations, we're producing very similar inputs, and that kind of causes us to take the same hot path a lot of the time. I wonder if you have any idea, like let's say I've identified that I want to do maybe a larger distribution of Havoc type mutations, which could, destroy and produce an entirely different looking input. So I'm wondering, like, if you think this kind of also depends on what sort of the distribution of mutations we're doing in our particular fuzzing algorithm, right? And whether it might hold if we're doing these more Havoc style mutations more often.
Yeah, for sure. So if you do mutations that like end up, like if you consistently do mutations that end up doing something completely different, that might be an issue. That might be also a way to inform, when you want to do the recompilation. If you see a lot of like Havoc style mutations that actually like result in weird new coverage, or if you see like a shift in what the fuzzer is doing, that might be a way to like pick out when you want to do this recompilation rather than just like going, okay, it's another hour, like let's recompile. However, I'm not like necessarily sure that you will actually end up with like a lot of test cases that trigger like new behavior, because even if you do a lot of Havoc, like I imagine most of them will end up in the same error path. And then you can still even if you optimize the error path, that's still okay. You don't want to do this in the real world because what are you doing? But if you're like triggering the error path a lot, then optimizing that is actually like fine.
All right. Yeah, let's thank our speaker for the great talk. All right, for our next talk, Leon will be telling us about the things that count coverage evaluation under the microscope. Yeah, go ahead.
Thank you for the introduction. This is joint work with Tobias, who just presented, and Kevin Vergolte from University of Bochum. Yeah, all of us do fuzzing, and all of us want to know whether what we're doing is improving the state of things and which of the stuff we're doing is better. And to do that, we usually do some form of benchmarking. And mostly we have converged in doing this using some type of code coverage-based benchmarking, like often FuzzBench, which is done by Jonas Mahathevan and also Laszlo and some others from Google. And it's mostly based on code coverage and uses LVMCOV for coverage. And we have observed that there are situations where it just does not add up what comes out of there. something very important first. This is not an attack on benchmarks. This is not an attack on FuzzBench or LVMCAF. The idea is let us try to see how good our results actually are in the sense of how reliable they are. So some motivation first. These numbers are from one of our FuzzBench runs on SQLite. And we looked into like the data more closely and we're like, this just can't be true. Like if we had done this, this would still run for like more than a human lifetime. So looking at this number more closely, we can see that it's actually 2 to the power of 64 minus 1. And we kind of wondered how that happened. And looking a bit more deeply into this, we saw that we have to look at how LVMCAF does coverage, and it basically splits up our code into these blocks. It does this on the source code level, and then instruments during compilation using some counters. And the important part is that it drops some counters where it can conclude or compute that from other counters. For example, here you can see that the function tail gets the same count as the if condition because there's no way you can exit before that, right? At least that's what the compiler thinks. And the same is true for branches. So the branch, like the then branch here must have been taken b times, and more importantly, the else branch must have been taken a minus b times. And now what happens is that if we look at SQLite, it basically has multiple threads, and in multiple threads, this function is being executed. And if multiple threads race for updating these counters, they are wrong. Well, they can be wrong. And in this case, we can see that if we subtract 1,535 from this 1,534, well, that is minus 1. So we have something that's wrong. And the important part here is that we basically think we have taken a branch that has never been executed at all. And that is bad for fuzzing evaluations, right? Because we don't want to count what has not been covered, but what has really been covered. And then we set out to like basically look at FuzzBench step by step and see what could go wrong else, or what does go wrong elsewhere, and to see what the impact of that is. So starting at the top, so to speak, of the pipeline, so the fuzzer fuzzes the target and writes all its test cases to disk. And FuzzBench periodically goes there and like collects all of the files on disk to then do coverage on that. The first issue there is that some fuzzers decide to write metadata files among their test cases. So basically collect coverage on files that have never been actually used for fuzzing, which is not great. Also, there's some issue with statefulness because some of these targets like carry over state between different inputs, and if the target restarts, FuzzBench doesn't know about it. If the test cases are reordered, FuzzBench doesn't really care. So at that point, we may hallucinate, or we do hallucinate, or drop branches that have actually been covered. Also, there's some issue that's not really related to FuzzBench. So there's like fuzzers only store files that are interesting to them. So the other files might have also, or do also, contribute to the state. So we cannot really like reconstruct the exact state the target has been in to like exactly count or collect all the coverage. Next up, we have now collected all our test cases or files, and now we need to run that through our instrumented target binary to like collect some coverage. And here we can see that, or we've already seen that in a motivating example, that we have miscomputations. For example, because there is racing for counter updates, but also there might be crashes in between different counters, and if we then do math, that's also wrong. Also, there's signal handling and set jump, long jump, which is like not visible to the control flow graph or to the compiler in that stage, so it makes assumptions that no longer hold if we have these. After we have now incremented all our counters, we need to write them to disk somehow to like persist them. And at that stage, we have like two parts where it could go wrong. One is what happens if we crash during evaluation. And fortunately, FuzzBench the Fuzzbench authors knew about that and fixed the libfuzzer runtime to also dump the counters if the target crashes. However, OSS-Fuzz, which Fuzzbench is based on, did not take that fix in. So there it's still broken. Later on, we merge all the counters from all the individual snapshots to not rerun all prior test cases again. But also that is fine because we have 64-bit counters, and overflowing them is very unlikely doing plain addition. So now we have counters or raw counters, which tell us something about how often each block is executed, but we don't know where the blocks are. And that is where LVMCAF uses some mappings, which it embeds into the target, like coverage binary. And using these mappings, it basically produces a report that's mapped back to lines, branches, regions, also, and so on and so forth. Here we have two issues again. One is that there's sometimes mismatched mappings, so like they do some hashing to ensure that they only connect counters to the correct code areas. But for some reason, there's some bug which we have not really found yet in Clang, where we have some mismatches there and we drop coverage. Also, there's some language constructs that are not handled correctly in Clang and just lead to incomplete mappings where also counters or counts are dropped. And finally, Fuzzbench takes this summary from LLVM and produces all these nice plots that we all know. And while doing so, it relies on the data from LLVMCAF, and LLVMCAF does something interesting. It summarizes instantiations. So if you look at the totals at the bottom of your report, all function instantiations of the same templated function are counted as one, and you only see the highest coverage of all of the instantiations. That might be reasonable for some use cases. For fuzzing, it's not, because we want to really cover all of the instantiations, right? Because after all, one might have an issue, but the other is not. Also, there's a slight mismatch in definition. So if we look at unique branches, LLVM takes both the then and the else branch as individual branches, while Fuzzbench takes them as one, which is also not great for the report. So in total, we have looked at all of these things and found 6 areas where we have some issues. And now the question is, does it even matter? Are these issues relevant in practice? So we did some preliminary experiments. And for example, for the statefulness issue, we looked at what happens if we keep the state across different test cases while evaluating, or drop the state after each test case. And we can see that, to no surprise, I guess, the stateless evaluation has less coverage than the stateful evaluation, at least for Hardfuzz in this case. For another issue, which was the instantiation summaries, we can see that the number of branches effectively halves, or almost halves, if you summarize instantiations. And what's more of an issue here is that looking at the ranking, what's the order of the fuzzers, we can see that using summarization, libAFL performs best, while looking at all instantiations individually, AFL++ performs better. And finally, for the unique branches, where we have this definition mismatch, we have seen that Fuzzbench sometimes reports that there's no difference in unique branches. Well, actually, there are some, and which is true for this over here. We have 12 versus null or 0. And in other cases, also again flips which one is better. These are preliminary results. So for the final experiments, we want to do this of more trials for 24 hours. Do this in all 23 Fuzzbench benchmarks with the 4, I guess, major fuzzers right now. And then address each of the issues we found in isolation, reevaluate on the fixed version, and see what's like the difference between the fixed version and the baseline. And finally, the question is, how large is the impact of each of these issues, and can this like flip rankings? How does this influence our previous experiments, basically? And with that, thank you, and I'm open to any questions.
Thanks. Any questions from the audience? Yep.
Thanks for the presentation. Very interesting. I don't remember the slide, but at a certain point, when you list all the problems in FastBench, there was something about state accumulation for libfuzzer. Yeah,
You mean this, or?
Yeah, probably yes. I didn't understand what's the cause of state accumulation. Is it because because it is in process fuzzing and the harness doesn't clean up the state? That's the problem.
Exactly. Like, I mean, not only in process, but also like persistent mode fuzzing and all of these, right?
Yeah, okay. So if you have a fork server, this should be mitigated.
If you don't do persistent mode, yes.
Yeah, exactly.
But like, you don't want to limit your fuzzers that you can evaluate to like fork server-based fuzzing.
That was not my point. My point was, is this a problem of FastBench or the harness? Because the developer just wrote a bad harness. I mean, it's not my fault, right?
Yeah, I mean, it is a fair question. I think the issue is that we need to be sure, we need to think about what we want to achieve, right? If we want to measure correctly what the fuzzer actually saw and actually covered, then we need to take state into account. If we say we don't care about what the fuzzer actually covered, but how good the like resulting set of test cases is that we have written to disk, the end state doesn't matter.
I completely agree with you. But if I realize that one harness is broken, I would just drop the harness from my evaluation because there's not significant for my case. The rest, I completely agree with the rest, right? But this specific point, I don't know. Yeah.
I mean, it is true. It's just something that we need to think about.
Absolutely.
And we need to like
come
to a common sense of what we want as a community. It's not a sense of like, this is the best version and this is like totally wrong. It's more of like, hey, this is an issue and we need to think about what's...
Yeah, I completely agree with you. Yeah, it was just different angle. How can we tackle this specific problem? If it's the system or is the developer or is we as choosing what to test? But yeah, I got the point. Thanks. It was very interesting, all these details.
I mean, it's like, that's the part of like, we don't want to attack any of these concrete systems, right? It's more of like, hey, we need to think about this when we do evaluations. I need to be aware of the potential pitfalls, or not potential because we have seen them. And as FuzzBench is kind of like not really maintained by Google anymore, I'm not sure what the current state of that is. And we need like some other benchmarking, as Matthias has also said this morning. Let's make sure not to like make these implicit assumptions again without like considering what's happening there.
Yep, I completely agree. Thanks again.
Any other? Yeah.
Yeah, this is fantastic work. Thank you so much for doing this. So it looks like some of the issues are coming from LCOV. And before LCOV, we actually used GCOV. One thing I was wondering whether you looked into if GCOV have the same issues, or we could resolve some of the LCOV issues just by going back to GCOV.
This has been a review question also. And I mean, some of them are definitely like basically linked to the things how FuzzBench is basically doing it. Others are very independent of that. And most of the like LVMCOV things are basically due to how they do coverage. And I don't know how GCOV does that, like internally. But we like have plans to look at basically would just swapping it fix it or not. But that's like future work for the final version.
Thank you. Yeah, and for your question. Like, don't give up on Fuzzbench yet. Like, we definitely want to keep it alive. And if you contribute, fixes for some of these problems like that,
we will should do.
Then we should make sure that those land and we keep Fuzzbench alive. Thank you so much.
Also, thank you for doing this. Right.
Any other questions from the audience? Quick question from me. So zooming out a bit, we'll read all these papers, we'll see the rankings, etc. I'm kind of curious how you got motivated to go deeper into these potential inaccuracies, right? Because in general, fuzzing very stochastic. We do multiple repetitions. We do 24 hours. Very, hard to tell like when something like this might be happening. So I'm just kind of curious how you sort of started with this project and got more into it and found all these different things.
We initially tried to look into which test case covered this specific area and to evaluate one previous project. And we couldn't just find one. I just reran all of these individually and it is not covered at all. What is happening here? And that led down to a rabbit hole, what's happening there? And then we looked at more examples and found this miscomputation example. We're how does that work? That's not plausible. Yeah. And then it kind of spiraled from there. Let's look at what else could go wrong and what's happening there.
Yeah, that's great. Yeah, I think sometimes we zoom out and look at it, look at fuzzing in terms of a black box in some sense, but it's very good to get into the nitty gritty and surface these things. So yeah. Let's thank our speaker again. And we can get the next speaker up. You may need to set up the mic.
Where's the mic?
I think they might be back there.
Tobias. Oh, yes.
All right, for our next talk, we'll have Tobias, who will be talking about type fuzz, type coverage directed JavaScript engine fuzzing. So yeah, go ahead.
Yeah, thanks for the introduction. Yeah, I'm a PhD student for roughly 9 months now, and my research is about browser security and fuzzing. I'm part of the Casa Excellence cluster, just like the 2 previous speakers. Yeah, and I'm from Bochum in Germany. Okay, moving on to the main content, I would like to start with an introduction to JavaScript engines. JavaScript engines are simply software that executes JavaScript, and V8 is the JavaScript engine that has the highest market share. That is because V8 is found in Google Chrome, the browser with the highest market share, but not just in Chrome, it's also found in any Chromium-based browser, for example, Edge or Brave. And apart from browsers, it is also found in applications such as Discord, Slack, or Teams. Yeah, so they are pretty much everywhere. And what makes them interesting from a security point of view is that they process entirely untrusted inputs, and it's fairly easy for an attacker to execute arbitrary JavaScript in a victim browser. And this is especially problematic because these JavaScript engines have a history of vulnerabilities. Now, if we use V8 or any JavaScript engine for that matter normally, nothing really interesting happens because that is what these engines were built for. they remain in this land of expected behavior. And the problem is that there might be some bugs. These bugs are hidden in rare locations that we simply do not reach in practice because we use the engine in such a limited way. And this is, of course, where fuzzing comes in. Doesn't need an introduction here, but we should mention that we use Fuzzily as a basis for this work. Fuzzily is suitable for our purposes because it's actively maintained and it can generate syntactically correct and semantically interesting JavaScript inputs. And the primary bug oracle it relies on are assertion violations in the engine, so primarily logic bugs. Like most fuzzers, Fuzzily relies on code coverage feedback, which allows it to reach these rare locations and find bugs that are hidden there. But the research question we are asking is if there are some bugs that are not just dependent on the location, but also on rare data. Now, the term rare data is a bit ambiguous as opposed to locations. For locations, we know what that means. Those are edges in a control flow graph or lines, but rare data deserves an explanation. And this is why I want to talk about V8's type system now. In V8, any JavaScript value, strings, objects, arrays, and even Booleans are allocated on the heap. Each of these becomes a heap object, and each heap object has a specific type. This is what we are looking at here. Each of these leaf nodes is a heap object type, and it's not really legible. This is why I want to show an example. If we zoom into here, these are 24 different types of strings, which is interesting because if we look at the ECMAScript language specification for JavaScript, there's only one single type defined for strings. So what's going on here? Why does V8 have so many types for strings? It is because of optimizations. And I want to show an example. For example, if we use string.slice, a naive implementation would simply return a copy of the substring, but this is time-consuming and space-consuming, and this is why V8 can or does use a copy-on-write approach, and to keep track of that, it uses a specialized type. Another optimization is to use a 1 byte per character encoding for the string, even though the ECMAScript definition says 2 bytes per character, or rather UTF-16 encoding. So these are just optimizations that V8 uses based on these types. So now we have an idea of what we mean with rare data. We mean these heap object types, and the idea of this work is to try and observe as many of these heap object types at as many locations that are security critical inside of V8. And to do that, we came up with a method, we call it TypeFuzz. The idea is to insert hooks into V8's source code in locations where heap objects are used, either because V8 needs to read from them or use them as a function argument or even change the heap object in some way. And each hook has a specific location. And when this hook is called, it looks at the type of the heap object, and based on this type of the heap object and the location of the hook itself, TypeFuzz calculates a unique index to a shared memory region for Fuzzily, so the bitmap. And this way, Fuzzily knows when new interesting data states have been reached. After applying our method, we ended up with 463 locations which are instrumented, and 2/3 of them are inside of Turbofan. This is the most aggressive JIT compiler inside of V8, and the rest of them are in maglev. This is the mid-tier JIT compiler. Now, I don't have time to introduce them, but the important thing about these two JIT compilers is just that this is where most of the vulnerabilities, or many of the vulnerabilities have been found in the past. And this is good for us because we have basically inserted our hooks into there. Yeah, and each hook can theoretically observe 313 unique types, which gives us an explorable state space of 150,000 units. Yeah. So let's look at the evaluation now. We have two research questions. The first one is, what's the achieved code coverage when using this new feedback mechanism? We get a slightly lower code coverage, which is an expected result, because we do not reward Fuzzily for reaching new code coverage. We can use a dual feedback mechanism. If we use both code coverage feedback and type coverage feedback, the code coverage basically stays the same. And regarding the throughput, we observe that our instrumentation does not really slow down Fuzzily. Actually, to the contrary, Fuzzily becomes slightly faster, or not Fuzzily, but the entire fuzzing pipeline, because we just instrumented 463 locations as opposed to code coverage feedback, which instruments like many more locations. Yeah, but the most important graph is probably this one. This is the achieved type coverage. This is what we wanted to optimize. And here we can see that when we use our custom feedback, we really do achieve much more type coverage, roughly 38% higher. So we can say, yes, we reached these rare data states and explored the state space more thoroughly. Now the question remains, did we find any bugs? The answer is yes, we did find 4 bugs, but the problem about this is that these bugs were also findable with code coverage feedback, so they were not really, their finding is not really attributable to our new feedback mechanism. And most of them were also short-lived, so nothing that was hidden inside of V8 for a long time, rather something that the team was already aware of at the time of finding them. So how can we improve this? We propose an extended evaluation consisting of 3 points. First, we want to employ the dumpling bug oracle that Matthias already introduced. But to recap what this is, it's a differential bug oracle that can detect JIT miscompilations. And the reason why we want to use this is because reachability does not necessarily mean detectability. We might have actually reached new bugs, but were unable to detect them because if there's no assertion, sometimes we can simply do not detect that there has been a miscompilation. And this is the problem that dumpling solves. And as Matthias already said, dumpling is now integrated into V8 and Fuzzily, so it's actively maintained, which makes it suitable for our purposes. And the next step would be to scale to other JavaScript engines as well. In particular, we want to also test JavaScript Core. This is the engine that's used in Safari. The benefit of testing JavaScript Core is that it also has a rich type system, which gives us a large explorable state space. And I already can hear the question, where is SpiderMonkey from Firefox? The reason why this is not there is not because we are lazy, but because the type system is rather small, and the explorable state space also, as a result, is also small. So it's questionable whether we would really find these rare data states. And the third idea is to invest more computing power because, in our preliminary evaluation, we observed that we can still make gains. And by tripling the duration, we hope to observe some bugs that are maybe dependent on ultra rare data states. Okay, with that, I would like to thank you and ask for your questions.
we have time for 1 or 2 questions. Can you expand a little bit on this hybrid approach of the coverage feedback plus the type coverage? And do you know if there's any like kind of way that you might want to explore this hybrid? It seemed like for the type coverage feedback, it seemed to outperform the hybrid approach, but I'm just curious, where you see that.
Yeah, so how it works on a high level is just to have a shared memory region just for code coverage feedback, and then after that for type coverage feedback. And regarding the code coverage, yes, we can basically restore the code coverage that way, but regarding the type coverage, we observed that it drops. So it's somewhere in between, which probably has to do with that Fuzeli is just really busy processing all the new code coverage inputs. So there's a trade-off there. Maybe if you have infinite computing power, then or can restart the fuzzer a lot of times, then it's also a matter of like fuzzing evolution. Sometimes restarting is necessary. So but for maximizing type coverage, using our feedback without code coverage feedback is definitely the best solution.
That makes sense. Thanks. Any other questions? Okay, let's thank our speaker. And we have our final talk. You can come get set up. Do you have a mic? Can you get your microphone? So for our last talk for session 1, Yining will produce UAV config fuzzer detecting incorrect configurations in unmanned aerial vehicles via set point estimation guided fuzzing. So go ahead.
Good morning, everyone. Due to visa issues, the authors are unable to attend the conference. Today, I will present the work UAV config fuzzer detecting incorrect configurations in unmanned aerial vehicles via set point estimation guided fuzzing on behalf of the authors. First of all, let me describe the background. Unmanned aerial vehicles, or UAVs, are commonly known as drones and can fly autonomously. Flight control software is the core system that governs the UAV behavior and ensures safe flight. To support diverse missions, flight control software such as PX4 provides hundreds of configuration parameters, including velocity and acceleration limits to customize UAV behavior. However, these configuration parameters introduce a severe challenge. Incorrect configurations can cause instability and even crashes. Therefore, detecting incorrect configurations is critical for UAV safety. Fuzzing is a widely used technique for detecting incorrect configurations. In UAV configuration fuzzing, the key idea is to mutate configurations and observe UAV physical states to detect anomalies. However, existing UAV fuzzer, such as RV fuzzer, rely heavily on simulators to obtain physical states. However, simulation is slow and severely limits fuzzing efficiency. Another approach, LGD fuzzer, uses machine learning models to predict physical states. However, these approaches depend on training data, such as flight logs, which limits their generalizability. This leads to a key question. How can we improve the efficiency of UAV configuration fuzzing without relying on simulation or training data? Our key idea comes from the internal design of flight control software. flight control software generates something called set points. Set points are target physical states, such as the position or velocity that guide the UAV motion. During flight, the UAV controller continuously follows these set points to guide the motion of the UAV. Therefore, set points represent the intended physical state of the UAV. This means that instead of running expensive simulations, we can directly analyze set points to estimate UAV behavior. This allows us to bypass simulation to gain a more effective fuzzing. Use set points, we can estimate the UAV physical states and detect anomalies. Based on this insight, we propose UAV config fuzzer. The input to UAV config fuzzer includes the source code, configuration parameters, and flight mission. UAV config fuzzer first mutates configuration parameters based on extracted constraints. It then uses the set point generator as feedback engine to estimate UAV physical states and detect anomalies. Finally, UAV config fuzzer outputs incorrect configurations and refines valid configuration bounds. The key novelty lies in the feedback engine. Instead of using simulation, we reuse the set point generation module to generate set points and estimate physical states. This enables fast and accurate feedback for fuzzing. Specifically, in the feedback engine, which is the core component of our design, we reuse the native position smoothing module from the flight control software and inject configuration parameters and flight mission into the module. The generator then interactively produces set points based on the UAV state and mission waypoints. Each generated set point represents the next target physical state, such as the position and the velocity. We update the UAV state using the generated set point and continue this process. Finally, we obtain a sequence of set points representing the UAV's physical states throughout the mission. This allowed efficient physical state estimation without simulation. We first perform static analysis based on the source code to extract configuration constraints. These constraints include configuration bounds and correlations. This helps reduce the search space and ensures more efficient mutation. Next, we perform two types of mutation. The first is 1D mutation, which mutates individual configuration parameters. The second is ND mutation, which mutates multiple correlated parameters. This allows us to detect both individual misconfigurations and interaction-induced misconfigurations. Next, we compute fitness score based on the generated set points to detect anomalies, such as rapid ascent, descent, deviation, or interruption. A higher fitness score indicates a higher likelihood of incorrect configuration. This feedback engine guides the fuzzing process toward configurations that are more likely to cause anomalies. After the fuzzing process terminates, UAV config fuzzer outputs candidate incorrect configurations. These candidates are then validated and the valid configuration bounds are refined. Let's see the evaluation. We evaluate the efficiency of the set point generator at a feedback mechanism. For flight missions with 10 waypoints, simulation takes about 28 seconds to estimate physical states. In contrast, the set point generator requires only 27 milliseconds. This achieves a speed up of more than 1,000 times compared to simulation. This significant speed improvement enables efficient configuration fuzzing. For the accuracy, we benchmarked the set points it produces against those generated by the native flight control software. We employed a 10-waypoint flight mission executed in the PIX4 with default configurations. As shown in the figures, we can see that the set points generated by the set point generator align closely with the ground truth. Finally, we evaluated the effectiveness of UAV config fuzzer. It successfully detects 14 incorrect configurations. Importantly, 5 of these were not detected by the state-of-art fuzzer. This demonstrates the effectiveness of our approach. To conclude, we propose UAV Config Fuzzer, a novel configuration fuzzing tool for UAV flight control software. Our key contribution is a setpoint estimation guided feedback mechanism. By resolving native setpoint generation logic, our method first eliminates dependency on simulation. Second, does not require training data. Besides, we achieve over 1,000 times speed improvement and successfully detects real incorrect configurations. That's all. Thanks for your attention. Please feel free to contact the authors directly if you have any questions. I will try my best to answer your questions.
Yeah, we have time for a couple questions. Any questions from the audience? So I think it seems like a lot of great work has been done on this set point generation component. And in my mind, that sort of idea is generally applicable to other maybe real world types of like robotics or maybe self-driving car scenarios. Do you think this idea could potentially translate to things outside of drones or UAV specifically?
I think that this idea is scalable since many peripheral work may rely on the simulation of the physical states, but we can use the code logic that generates the set points that effectively to estimate the physical states without simulation.
Okay, yeah, that's very cool. Any other questions? All right, I think we can thank our speaker. Thank you for presenting for the authors.